Hello, I'm Hilson Shrestha from Worcester Polytechnic Institute. In this short paper, we present a system called FairFuse, an interactive visual support for fair consensus ranking. Decision making by forming a committee is really common in our society. A group of stakeholders put forward their opinions and discuss together their preferences to form a consensus. A type of such consensus building involves the use of rankings. Let's take an example of such a scenario. Imagine a group of students in a school who are qualified to get some form of scholarships. The school has a committee with 3 teachers, math, reading and writing, that looks after the scholarship distribution program, and you are the head of the committee. Each teacher has their own preferences of students based on their performances in their subjects and other attributes like assignment completion. Now, as a decision maker, you need to combine the ranking preferences of all the teachers and get a single consensus ranking, which is a really complex task. Now, to complicate things even further, we have attributes like race, religion, or gender, as in this example here. These attributes, also known as sensitive or protected attribute, cannot be discriminated against. The rankings made by the 3 teachers could be biased with respect to such attributes, favoring male candidates over female candidates. You now have a bigger problem of not just ensuring that you generate a ranking that best represents rankings made by all the teachers, but also making sure that it is fair to all gender groups. Here are some of the tools that can be used to generate consensus rankings or generate and analyze rankings in general. Now, we want to extend the consensus generation process to include bias mitigation algorithms. In the fairness community, the predominant mitigation to bias is the notion of group fairness. Group fairness is conceptualized as treating groups similarly. And in the scenario we showed earlier, the goal is to treat all gender groups equally while ensuring that we still maintain certain level of consensus. And a possible fair consensus ranking could be something like this, where male candidates is not over-advantaged. One of the recent works in this field is the work by my colleagues Cachel et al., which introduces metrics and algorithms to aid decision makers combine multiple stakeholder rankings into a fair consensus ranking. 2 of the metrics introduced are the FPR and the ARP scores. Favored pair representation or FPR score is the measure of treatment of each group in the ranking, and the attribute rank parity or the ARP score is used to quantify if the overall ranking across all groups satisfies the statistical parity fairness criteria. In the example earlier, the FPR score gives the advantage a male or a female group has in the ranking, and the ARP score gives the overall fairness measure of the ranking considering both male and female groups. Extending on this previous work, in this paper we present visual encodings for group-based fairness metrics, design and development of FairFuse system itself, and case studies to demonstrate how a decision maker can use FairFuse in fairness-oriented ranking scenarios. Now let's take a look at the FairFuse system itself. FairFuse is designed to support the process of both analyzing and combining preferences from multiple rankers into a fair consensus ranking. First, we have the ranking exploration view. This view displays the provided base rankings made by individual stakeholders and also the generated consensus rankings. Each candidate being ranked has a set of attributes and a protected attribute like race. The largest square on the left represents the protected attribute with color denoting the candidate's attribute membership, for instance, white in the race protected attribute. All other small shapes represents non-protected attribute with color also denoting the candidate's values in those attributes. Each candidate appears across all rankings with lines connecting them. Lines are colored based on the degree of change in the candidate's position between adjacent rankings. Next, we have the group fairness view. Say we have a ranking of 100 candidates and 5 race groups, and we want to identify a disadvantaged group. It would be really difficult to identify such groups just by looking at a ranking. So to illustrate the level of advantage a group has over other groups, we separated out each group into their own column. Each group is represented as a colored dot like white, native or black, and its position indicates the FPR score. Dots above the 0.5 FPR line indicate that the group is over-advantaged, while the dots below the 0.5 FPR line indicate that the group is under-advantaged. In this example, the group represented by the purple dot is over-advantaged and the group represented by the orange dot is under-advantaged. The difference between the most advantaged and the least advantaged group is colored in gray. The size of this gray box gives the level of bias present in the ranking, also known as the ARP score. Thinner gray boxes indicate fairer rankings. The colored heat map on the side of each dot displays the distribution of candidates belonging to the color-associated group. The Generate Consensus Ranking button is used to generate a fairness-unaware consensus ranking. This gives a ranking that best represents base rankings and is displayed on the far right of the ranking exploration view. The generation process will then have a slider that allows us to incorporate fairness in the generated consensus ranking. Moving the slider to large fairness threshold values creates fairer consensus rankings. These fairer consensus rankings will have lower ARP score, as represented by the thinner gray box. However, as we increase fairness, we start losing agreement of base rankings in the generated consensus rankings. So with the help of similarity view, we attempt to show agreement between any two rankings with darker squares denoting higher similarity. This view, along with the parallel coordinates plot in the ranking exploration view, enables us to analyze dissimilarity between rankings and provide an intuition on adjusting fairness threshold or reposition the candidates as needed. Finally, the ranking exploration view can be toggled between a normal view and a compressed view. The compressed view allows more candidates to be viewed at once. While this work currently focuses on single protected attribute, future work could extend the visualization system to support multiple protected attributes and their intersectionality. Next, the future work could explore how to support multiple algorithms in a single tool, and also comparison between them. Another possible direction is to conduct user studies to explore ethical issues surrounding the algorithmic fairness. Thank you.